So we've been talking about hypothesis testing. The whole point of hypothesis testing is that we have some idea or some claim about the whole population of interest, and we want to make a conclusion about that claim for the population by using one or more samples. So, as an example, let's use a new example from yesterday. So let's say that our claim, let's say that you're administering a website. And let's say that you happen to think that your website is quite popular, and your claim is that at least 70% of all internet users have visited your site, let's say. So at least 70% of all internet users visited your site. So to test this claim, we have an observation in the form of one or more samples. And let's say your observation is that you have a random sample of, let's say, 1,000 people. And let's say in the sample of 1,000 people, let's say 731 people have used the site. So the question is this observation good enough for you to make a conclusion about this claim? Can you now make a definitive conclusion as to whether this claim is true or not? And we're going to use hypothesis testing to make a conclusion about this claim for the population. So last time we talked about the formal steps of hypothesis testing. Let's go ahead and review together. So what was the first step of hypothesis testing?
Identify the null hypothesis and the alternative.
Very good. So identify the null hypothesis and the alternative hypothesis, or in mathematical symbols, identify HO and H1. So the way that we identify those two statements is we start with the original statement we started out with, and that always has an opposite statement that we can call in the counterclaim. And there's many ways to phrase the opposite of at least 70% have visited the site, but the easiest way, the way to least make mistakes, is to keep this number the same, 70%, but change all the inequalities. So in this case, at least means 70% or more. So the mathematical symbol for the inequalities would be equal to or greater than, would be at least. So the counterclaim is going to involve all of the symbols that are left over. So that'll just be less than 70% have used the site. So the counterclaim, or the opposite statement to the original claim of at least 70% of internet users have used the site, the opposite to that, or the counterclaim, would be that strictly less than 70% of all internet users have used the site. Okay, so now that we have the two statements, the claim and the counterclaim, one of them will be HO, the null hypothesis, and the other one will automatically be H1, the alternative hypothesis. So now we just have to identify which is which. So in order to do that, we're going to convert each of these English statements into mathematical language. So for the claim, for example, we're going to use the symbol P which in the past we've said represents the proportion of success in the population. So success is what we're keeping track of, in this case, having visited the site. So P is the proportion of the population, or all internet users who have used the site. And the claim says that P is greater than or equal to 0.7. And the counterclaim, mathematically, P will be strictly less than 0.7. So we've converted each of these English statements into mathematical statements. And so the next step now to identify the null hypothesis will be to identify the statement that has the equal sign. So which statement has an equal sign? Yeah, the claim. So the statement that has the equal sign, in this case the claim, will be the null hypothesis. And the other one automatically will be the alternative hypothesis. And the reason we choose the statement that has the equal sign is because equal means that it's equal to one exact number. And that one number, we can build a model around that one number. Versus if you don't have equals, if you have P is less than 0.7, for example, then P can be anything as long as it's 0.7. It can be 0.6, 0.5, 0.2, 0.168, and so forth. So it can be infinite number of values, and you can't latch on to any one of those values. So we latch on to a statement that has the equal sign. So because of that, the null hypothesis itself, actually we can go one step further and strip away everything except for the equal sign, and the null hypothesis itself is just P equals 0.7. So technically, the null hypothesis is just the statement that has the equal sign, and that came from the inequality previously that contained the equal sign. So, all right, any questions? So now we have the null hypothesis, we have the alternative hypothesis. So now we're ready for step 2. So step 2 will, what's step 2? From last class.
Assume HO is true.
Good, very good. So assume HO is true. So in this case, what it means to assume HO is true is that we want to assume that P really does equal 0.7. And so the next step is to visualize this assumption with a distribution. So on the x-axis here, the x variable will represent the number of successes out of a total number of trials. In this case, a number of people who have visited this site. I'll just say number of successes out of the number of trials, which is out of 1,000 people. So if it's really true that the null hypothesis is correct and P really does equal 0.7, then if we're observing 1,000 internet users, then how many of those should we expect to be, quote, successes or having visited the site with the most likelihood? So if it's true that 70% are successes, then how many people out of 1,000 are we expecting to be successes?
700.
Yeah, 70% of 1,000, which is 700. So at 700, we should expect the greatest likelihood of observing that number of successes, and visually, the height of this bar will be the highest compared to all the other numbers. But of course, it doesn't mean that every time we observe 1,000 people, we're going to get exactly 700 successes or 700 people observing, having visited the site. So we could observe 701 people, but the probability is a little bit lower, so the height of this bar is lower. So as we move away from 700 in either direction, we'll see a distribution that tapers off, moving away from the mean of 700. So this is the visualization of this assumption that HO is true and P really does equal 0.7. And so what we want to also do to visualize this is to remember the whole point of this was to determine ultimately whether the observation of 731 is that considered consistent with this distribution or not, i.e. is it in the body or the tail of the distribution. So the next thing we need to do then is visualize the size of the area of the tails of this distribution. So let's say that we want a conclusion where the confidence level is
Thank you.
let's say 95%. So that's the confidence level itself. So the confidence level always pertains to the size of the body of the distribution. So the body is the area minus the tails. So that means that the tails add up to how much?
5%.
Yeah, the tails add up to 5%. But another word for saying the tails that's alpha. So alpha is the total of all the tails adds up to 5%. But remember, last class, we also said that in hypothesis testing, you can have either one tail or two tail hypothesis tests. That means that alpha either is on one tail or is that it's divided across two tails. But it turns out that it's really easy to determine whether we have a one-tail test or a two-tail test. So the way that we do that is we always look at H1. So from step one of hypothesis testing, this was H1. And then we look at the number of inequalities involved in H1. So the number of inequalities here is only one inequality. So this is a one-tail test versus a two-tail test. So had it been P is less than 0.5 or P is greater than 0.5 here, then that would have been a two-tail test. But here, as it stands, this is a one-tail test. And not only do we know this is a one-tail test, but it turns out that this is left tail because this is P is less than, so less than is to the left on the number line. And you can also draw out a little arrow on the inequality here that tells you it's pointing to the left and this is the left tail. So this is a left tail test. So that means that you can go ahead and draw out the one tail over here. And so all the tails have to add up to alpha, which is 5%, what's left from the confidence level. So because there's only one tail, then this tail has the full 5%. So alpha, or all the tails, add up to 5%. In this case, there's only one tail. And then the confidence level pertains to the body of the distribution, which is this total blue area. That's going to be the 95%. Yeah.
So to determine whether it's like a left tail or a right tail, we have to look at the alternative one.
You look at the alternative hypothesis always, and that's H1. Yes. Okay, so now that we know the size of the tails of the distribution, now we're ready to go on to the next step, which is to answer the next question. And this step actually involves the observation itself. So notice so far we actually haven't involved this observation of 731 in our sample yet. So now we involve it in answering this question of, is the observation consistent with the idea that HO is true? So we said that you can answer this question one of two ways, either yes or no. So if you answer this question as yes, the observation is consistent, visually, what does that mean? So if the observation is consistent with HO, what does that mean visually in the picture? Yeah, it's in the body of the distribution. So yes means that the observation is in the body of the distribution. And no means that the observation is in the tail of the distribution. So you have this exact correspondence. So in this case, again, we're trying to basically determine whether the observation is in the body or the tail of the distribution. So the observation is going to be 731 who visited the site. And in the picture, you know the mean is at 700, we determined that. And so 731 is going to be to the right or left of the mean? The right, because 731 is a greater number than 700, so it's going to be over here, let's say. So just by looking at the picture, without even doing any more math, can we determine whether the observation is in the body or the tail of the distribution? Yeah, it has to be in the body, right? Because this is a left tail test. The tail is to the left of the mean, and our observation is to the right of the mean. So our observation can't possibly be in the left tail. So our observation has to be in the body of the distribution. So you can already conclude that the observation is in the body of the distribution, and therefore the observation is consistent with the idea that HO is true. So now we can go ahead and actually formulate a conclusion without having to actually do any math. But we're going to go back later and actually do the math later. But for now, let's go ahead and formulate the conclusion. So you have one conclusion, and you have one observation here that is consistent with this idea that HO is true. So you have an idea, you have an observation that is consistent with this idea. So can you accept that the idea is true for all possible observations, just because it's consistent for this one observation? No, you can't just accept the idea. So we talked about this last time. So you can't accept the idea. Because just because the observation is consistent for the idea doesn't mean that all future observations will also be consistent with the idea. So you can't just accept that the idea is true for all observations. So the best you can do is not throw out the idea. Continue to hold on to the idea and observe more things and see what happens. So another way of saying that is we don't reject the idea, or there's not enough evidence to reject the idea. So for now, I'm just going to say fail to reject the idea. And the idea in this case is HO. So we're going to fail to reject the idea or fail to reject HO in this case. So that means we're not going to throw out HO yet. HO can still be true. We're not going to throw it out. That's all we're saying. And remember that fail to reject HO doesn't mean that we can never reject HO in the future. It just means based on this one sample, we're not going to reject HO yet. And it also means that we don't have enough evidence yet to be able to reject HO. So we're going to keep needing to have more evidence and observe more things before we can possibly reject HO in the future. So for now, we're saying that we don't have enough evidence yet to reject HO. Okay, so the conclusion here is fail to reject HO. So that is a correct conclusion in terms of HO. But remember, we always want to bring the conclusion back to the original claim. Because the claim is what we started out with. HO and H1 were manufactured by us. So, what correct conclusion can we make about H1 if we fail to reject HO?
Fail to accept it?
Yeah, very good. So the opposite of fail to reject will be fail to accept. And remember, we talked about the intuition for this. So the top one, fail to reject, doesn't mean accept, but we can think of it as leaning towards accepting. And vice versa, fail to accept doesn't mean reject, but we can think of it as leading towards rejecting. Okay, and so now that we formulated the conclusion correctly, one in terms of HO and one in terms of H1, we always want to bring it back to the original claim. So in this case, is the claim HO or H1? Yeah, from the first step of hypothesis testing here, the claim was HO. So we're going to look at what we said about HO, which is fail to reject HO. So we're going to say that about the claim here. So we're going to say we're going to fail to reject the claim, which means that doesn't mean we're going to accept the claim, but we're going to lean towards accepting the claim until further evidence. Any questions? Okay, so here we were able to reach these left set of conclusions because we knew that the observation had to be in the body of the distribution, not the tail. But usually it's not this obvious. So usually, what would we have to do to quantify in order to determine that the observation, whether it's in the body or the tail? Yeah, we'd have to compare two measurements. We'd have to compare, in this case, two z-scores. One is a z-score for where the tail starts. We call that the critical z-score. That's this line here. That has a z-critical. And the other z-score is the z-score for the actual observation that we call the test z-score, or z-test. So usually we compare these two z-scores in order to correctly quantify whether the observation is actually in the body or the tail. So in this example, we know the observation is in the body, but let's go ahead and go through this process of comparing these two measurements. So how would we find z-critical?
We would need to use the table.
Yeah, excellent. So any critical value, like this critical z-score, we're gonna use a table. So go ahead and consult the z-score table. And again, the way the z-score table is laid out, it has a relationship between z-score and area to the left of that z-score under the bell curve. If you know one, you can find the other. So in this case, we're trying to find the z-score. So if you knew the left area, you'd be able to find that z-score. And it turns out that we do know the left area. It's 5%. So we're going to look up a left area of 5% and find the corresponding z-score.
Negative 1.4, or negative 1.645.
Okay, great. So it should be negative 1.645. Go ahead and make sure that you find it. If you have questions, feel free to let me know. So we want to find the number 0.05 that represents the left area, and we want to find the closest number to 0.05. It turns out this number searches for so often that you'll be able to find it exactly. Okay, everybody find it okay? Alright. Okay, so this z-critical then is negative 1.645. And then that's the z-score for where this tail actually starts. And so let's find the z-score for our observation of 731 now. And remember, any test statistic, or test z-score in this case, will come from a formula.
Do you want to speak for it?
Yeah, so this is going to come from a formula. So let's talk about the formula. So remember, we talked about in class a formula for the z-score, the test z-score, but your homework will show you a different formula even though you'll get the same result. So in class, we talked about this formula. and we can practice using both if you want. So the class formula is this one. So X is the number of successes in our sample, which turns out to be 731. N is the number in our sample, that's the 1,000. P is the true proportion of all internet users who have visited this site. So what do you think that is? Yeah, very good. So it turns out that we don't actually know what that is. So we know the percentage of internet users who have visited our site from this sample of 1,000, but we don't know the percentage of internet users who have visited the site in the entire world. So we don't know what that is, but there's a step in hypothesis testing that we're assuming that HO is true. And that involves a population measurement here. So we're assuming that the true population measurement here is actually 0.7. And so we're gonna use 0.7 for our P in the formula. So that'll be 0.7 here, and then divide by the square root of NPQ, where N is 1,000. P is the true proportion who have visited the site. Again, it's 0.7. And Q is going to be 0.3. So if you punch this in, what's the z-score? 2.14. Alright, so this ends up being 2.14. And so that's calculating the z-score using this z-score formula that we talked about in class. But on your homework, it'll show you a different formula. So let's go over that formula and verify that we're getting the same answer. So the formula on the homework is this one. So it's this formula is p hat minus p all over square root of pq over n. And so if you play with the numbers there, let's practice. So what would p hat be in this case? P hat is the proportion of success in the sample, hence the hat. So that'll end up being 731 divided by 1,000. So this p hat will be 731 divided by 1,000. That's p hat. And then what's p? Same p we used before, which is assuming that HO is true. P is 0.7. And then the bottom numbers are the same as in the other formula. P is 0.7, Q is 0.3, N is 1,000. So if you put this formula in, you'll see that you get the same answer as before. You'll get exactly 2.14 as well. Alright, so now that we got the test z-score using any one of these two formulas, we can compare it to z-critical, which we got from the table, and we compare the numbers to decide whether the observation is in the body or the tail. So this z-critical is telling us that there's one left tail, and everything to the left of this critical value of negative 1.645 is inside the left tail. But our observation has a z-score of 2.14, which is to the right of that critical z-score, so therefore it can't be in the left tail. And so it has to be in the body of the distribution. And so now we reach the same conclusion we did before, because in the body of the distribution, we fail to reject HO, fail to accept H1, and because our claim is HO, we fail to reject the claim. Any questions? And again, failing to reject the claim doesn't mean we can never reject the claim. it means that we don't have enough evidence now to be able to reject the claim. So it means that basically we have, we're kind of in limbo. We can't reach a definitive conclusion, so we need to continue to observe more samples, more things. But let's say the observation, in this case, was in the body of the distribution. Let's say it had been in the tail. So let's say that we had observed a very small number. Let's say we had observed, let me make up a number, like 124. All right, so our claim is that at least 70% have visited the site, but yet only 124 out of 1,000 in our sample have. So that's what percent? That's 12.4%. Yet we're claiming that at least 70% have visited the site. So with this new number, do you think that would be in the body or the tail of the distribution? Yeah, it would likely be in the tail, and we can verify that by calculating the z-score of this test point. And we'll see that it's so far from the mean that it's going to be in the tail. Okay, so if it's in the tail now, what conclusion can we make? So we have this observation that is not consistent with this idea of HO being true. So if we have an observation that is not consistent with the idea, what can we say about the idea being true for all observations, not just this one?
You reject it.
Yeah, you can go ahead and reject the idea. So you can reject that the idea is true, because already it wasn't true for this one. And when you say rejects, that means that right now, you can go ahead and just reject. That means that you don't need any more evidence. So another way of saying that is that there's enough evidence already to be able to reject this idea. And if you can reject HO, what can you say about H1? You can accept H1. So both these are very strong conclusions. There's enough evidence already to reject HO, there's enough evidence already to accept H1. So in this case, the claim is HO, so we can say that we can reject the claim that at least 70% of internet users have visited the site, because in our sample, only 124 people have. So we can go ahead and reach a very strong conclusion and say there's enough evidence already to be able to reject the claim. And of course, any conclusion you make is going to have a caveat. It's going to say, we can say with 95% confidence, because that's our given confidence level, we can say with 95% confidence, we state these conclusions to reject the claim with 95% confidence. Yeah.
Couldn't you not technically, like, fully reject it? Cause what if just in your sample of 1,000, you just somehow got a large quantity of people that don't visit that site, but realistically the population is still like 70% have?
Okay, so that's a very important question. So it turns out, so the question is, what if you just happen to have a bad sample? Well, it turns out the answer to that question is, that's why it's important to have a good sample. And that's why we talked about what it means to be a good sample. So we talked about how our sample needs to be large, and it also needs to be representative of the population by being random. So if you feel confident enough that you have gathered a good sample and it's random, and so because your population represents all internet users in the world, that means you have to be certain that you randomly sampled from all internet users in the world. So it needs to be random in all aspects. It needs to be random geographically, it needs to be random in habit, in gender, and so on. So everything about the sample needs to be random. So good question. Any other questions? Yeah.
So, like, how can you tell whether it's like fail to reject or fail to accept?
Okay, so any hypothesis test we have, we're gonna either have this left side of the conclusions or the right side of the conclusions. The left side of the conclusions is always fail to reject HO, fail to accept H1. Right side of the conclusions is always reject HO, accept H1. So if your observation is in the body of the distribution, then you reach the left side of the conclusions. If your observation is in the tail of the distribution, always the right side. Because if the observation is in the body, that means that the observation is consistent with the idea that HO is true. And it's in the body of the distribution, so it's on the left side.
So it's both?
Yeah, both these are true,
Okay.
but the final answer, the final conclusion that you want to state is the one that involves the claim itself. And the claim will always be either HO or H1, depending on step one of hypothesis testing. So in this example, the claim happened to be HO.
Oh,
Yeah, so then you find the final conclusion you state is because the claim is HO in this case, then you fail to reject the claim.
Could there be a statement that says fail to reject H1?
Yes, a good question, so the answer is no. So any conclusion you make is only one of these four. So because step two of hypothesis testing here was that you're assuming HO is true, so the only idea you're considering here is HO. So this whole model was based around this model you're considering, which is HO. So either you can only reject HO or reject HO. Only these possible two, and vice versa with H1, you can either accept H1 or fail to accept H1. So there's no other possibility.
So, will HO basically always be the claim?
No. So the question, so HO is the statement that has the equal sign. So coincidentally, in this case, the equal sign was the claim. But in the example we did yesterday, for example, the counterclaim happened to be HO. Because we had the coin and we wanted to know whether the coin was unfair or not. And it turned out that the claim was that the coin was unfair, the example we did yesterday, and the counterclaim ended up with the coin being fair, which is P equals 0.5, and that ended up being the null hypothesis HO, and that was the counterclaim. So the null hypothesis is always the statement that has the equal sign. Sometimes it's the claim, sometimes it's the counterclaim. Any questions? All right. Okay, so this is a review of what we talked about last time with hypothesis testing. So now let's introduce some new material that's related to this. So remember, really, the whole gist of this, all of this reduces down to us looking at an observation and trying to determine whether that observation was in the body or the tail of the distribution, and then everything else followed. Now, one way to accurately do that is to compare two z-scores, to the test statistic versus the critical statistic. And the critical statistic always comes from a table, the test statistic always comes from a formula. And so let's summarize that.